Okay, well, so far we've mostly discussed static fluids, right? Just water at rest sitting in a swimming pool, and you dive deeper and the pressure increases. Right, so that's what we've discussed so far. Now we're going to turn our attention to moving fluids, dynamic fluids, right? Fluid dynamics. So there's some nice examples of this on this page. Of course, just water flowing through a pipe. That's fluid dynamics right there. It's really important for any kind of mechanical or civil engineering. It's really important for chemistry. It's really important for forensic science. Just understanding water flowing through tubes is really important. Okay, but on the lower left, you can see that in a lot of fields, fluid dynamics gets much more complicated. Right, the aerodynamics, the way the air flows over a moving car, is really, really complicated and really fun. So I hope you get interested in this topic and spend some more time learning it. And on the right picture, this is just clouds moving past an island, and you can see all these fascinating vortices in the clouds called von Karman vortices. So as you can tell, fluid dynamics can get really interesting and really complex, and is a really fun topic. So to start our discussion, let's talk a little bit about fluid flow, and we're going to talk about kind of two different types of fluid flow. The first is laminar flow. This is when the adjacent layers of fluid slide smoothly past each other in a steady state. So as a function of time, the flow is very steady. If you look at one single atom or one single molecule in that water in that pipe, that molecule is just flowing in a straight line. Right? That's what we call laminar flow. And so you can see laminar flow coming out of this faucet, and also this very clear laminar flow going over this airplane wing. Okay. The other type of flow is turbulent flow. In turbulent flow, there is no steady state pattern. The flow is kind of continuously changing and twisting and turning, and it's a little bit more complicated, right? So in turbulent flow, one single molecule of the water is kind of going in all directions and turning back at times and twisting around, right? So that's turbulent flow. Um, Again, if you turn up a faucet a little bit more, once you increase the flow rate, the faucet starts to be somewhat turbulent. Or if you look at just a match very close to the match, you can see maybe some nice laminar flow. But as the gas kind of gets higher and higher, you get this turbulent complex flow. Okay, so that's turbulent flow. And we can look a little bit more closely at an airplane. Again, an airplane wing will hopefully have nice laminar flow moving over it. But if you look at the landing gear of an airplane, obviously it's not very aerodynamic, and you get this very complicated turbulent flow behind it that if you want to understand and simulate, you need actually really complicated differential equation solvers. You need computational fluid dynamics. So you could have your whole career be based on just simulating this type of flow. Okay, and here even just a cube moving through the air, you get turbulent flow behind it. Okay. One other topic to discuss is viscosity. Viscosity is the internal friction in a fluid, right? So, for example, there's friction in some fluids from molecule to molecule, and also between molecules in the fluid and the edge of the pipe, right? So when a viscous fluid flows through a pipe, the speed of the fluid is actually greater in the center of the pipe than it is at the edge of the pipe, because the fluid at the edge of the pipe is interacting with the pipe, and that's slowing it down somewhat. Okay, so you can think about some viscous fluids you've probably interacted with, like honey. Right? Honey is very viscous, but hopefully you haven't interacted with lava. But lava is another example of a viscous fluid. And like many viscous fluids, the viscosity depends on temperature. Right, so the hotter lava flows more easily than the cooler lava. Right, so the viscosity changes based on temperature. Okay, so once we've introduced those topics of laminar flow, turbulent flow, and viscosity, we can start really learning the basics of fluid flow. And we are going to start by understanding the idea of flow rate and then something called the continuity equation. And we're going to restrict ourselves to basically low viscosity fluids, things like water, things that don't have all that much interaction. We're basically going to ignore viscosity and resistance for the beginning part of this chapter, and also steady state laminar flow. Okay, so basically we're going to have a completely filled pipe with water flowing through it and try to understand that system, and then we'll try to expand outward from there. So, okay, first, how do we measure flow rate? Well, there's two ways we can do that. One is called volume flow rate, and so this should make a lot of sense. It's just what volume of water is passing a given point in a given period of time. So if I just pick this point right here and look at this kind of cross-sectional area of the pipe and just measure how much fluid is passing that point every second, right? Is it 10 gallons per second? Is it 5 liters per second? And just how much is it? Some amount of volume every second. Okay, so that's volume flow rate. The symbol we use for that is dV/dt. This is a capital V, right? It's just the change in the volume with time, or how much volume of water is passing a given point in a given period of time. And so the SI units for volume are meters cubed, right? The SI unit for time is seconds, so our unit for volume flow rate is meters cubed per second. But you will likely see in problems other units such as liters per second or gallons per second, etc. Okay. Another way you can measure flow rate is the mass flow rate. Instead of measuring how much volume is passing a given point in a period of time, you can measure just how much mass of fluid, right? How many kilograms of fluid are passing a given point in a given period of time. Obviously, mass flow rate and volume flow rate are very related. They're related by density, but you will see mass flow rate on occasion. So the symbol for mass flow rate is dm/dt, and the units are kilograms per second. We'll likely use this a little bit less often than volume flow rate, but I wanted to introduce the idea anyway. Okay, so looking a little bit more closely at volume flow rate, we can actually drive a pretty important formula for calculating the volume flow rate. Right, so you may not have a meter which can tell you how many gallons per second are passing a given point, but you may be able to measure the velocity of that fluid, and you may be able to measure the cross-sectional area of your pipe. And it turns out, if you know those two things, you can calculate the volume flow rate. In fact, if I look at this volume of water and measure it's moving at some velocity v, and if I know the cross-sectional area of this pipe, A, it turns out that the volume flow rate, dV/dt, is equal to just the area of the pipe times the velocity of the fluid. Okay, and you can check this on your own with just the units, right? The area of this pipe is measured in meters squared. The velocity of the fluid, v, is measured in meters per second. So multiplying those units together, we get meters cubed per second, which is our unit for volume flow rate. Right? So it turns out the amount of volume passing a given point in a given period of time is related to the cross-sectional area of the pipe and the speed at which the fluid is moving. Okay. So now let's try to understand how volume flow rate changes and how velocity of fluid changes as you change the size of a pipe. If you make a pipe bigger or smaller, what happens? So let's start with a quick observation. If I have a hose, there's some amount of water coming out of my hose at a certain speed, and then I put my finger on the end of the hose, and I'm sure everybody has done this before. When you put your finger on the end of the hose, the water sprays farther, right? And it's flying in projectile motion. If it's going farther, that means it's moving faster at this point, right? So somehow by putting our finger on the end of the hose, we've increased the velocity of that fluid. So here's just a quick question, a conceptual question. You can think about it on your own and then move on to the next slide. Why does the velocity of the water increase when you put your finger on the end of a hose? Okay, is it A, you're increasing the pressure of the water by putting your finger on the end of the hose, or is it B, water is an incompressible fluid and it must move faster to keep the flow rate constant? So think about that, pause the video, and when you're ready, move on to the next slide. Okay, and it turns out the answer here is B. You're not increasing the pressure of the water when you put your finger on the hose. In fact, the opposite is happening. Turns out the answer here is that water is an incompressible fluid, and in order for it to keep its flow rate constant, it must move faster. Okay, one way to think about this is if there's 1 gallon per second coming out of the hose, that's not going to change because there's 1 gallon per second moving through every part of that hose, and the hose is completely full with incompressible fluid. Right, so that 1 gallon per second needs to keep coming out of that hose, and if you restrict the opening, the water has to move faster in order to keep that 1 gallon per second going. Okay, so hopefully that may give you a bit of a hint to this answer, but think through this answer also. If you were to fill up a bucket with a hose, which would take longer? A, filling up the bucket with no nozzle on the hose, so that's just the picture on the left. Or B, filling the bucket up with a nozzle or just your finger on the end of the hose. Or C, it will take the same amount of time. Okay, and so the answer here is C. It'll take the same amount of time. Right? So what that means is we haven't changed the volume flow rate. The volume flow rate does not change when you decrease the size of an opening or increase the size of an opening, or if the volume flow rate is not changing in that pipe. Okay, so this is going to lead us to a very important idea called the continuity equation. Okay, so basically, if I have a pipe, it has some cross-sectional area. I can look at one volume of water. Maybe this area kind of dark, that's dark purple here, is, oh, I'm sorry, I labeled it 1 liter. Let's call it 1 liter of water. Okay, that 1 liter of water is flowing in this direction at some velocity, and then all of a sudden the pipe gets smaller. Well, there's 1 liter of water behind this one, another liter of water behind this one, all moving at the same velocity. So when this pipe gets smaller, all of a sudden it can't just stop, right? So what happens is it needs to kind of spread out and move faster in order to keep this 1 liter per second flowing past any given point in a given period of time. So if I look at point 1, there's 1 liter per second passing that point. If I look at point 2, there's 1 liter per second passing that point. In order for that to happen, the water must be moving faster when you make the pipe smaller. All right, water is completely incompressible. It's a completely filled pipe. All right. So how do we say this in an equation form? Well, what we're saying is that the volume flow rate is constant, and here's an equation for that. The volume flow rate, dV dt at point 1, is equal to the volume flow rate at point 2. Okay, so that's all there is to the continuity equation. The volume flow rate in a pipe that's completely full with an incompressible fluid has to be the same everywhere. If you put 1 gallon in this side of the pipe, 1 gallon has to come out of this side of the pipe, no matter what. There's no more room in that pipe for anything else. Okay, so this is our continuity equation, and we learned a few slides ago that we can rewrite the volume flow rate in terms of the area of the pipe and the velocity of the pipe. Right? And so this becomes a somewhat more useful equation when we do that, when we rewrite the volume flow rate as area times velocity, because these are things that are easy to measure. You can measure the velocity of the water in this part of the pipe at point 1. You can measure the cross-sectional area of the pipe at point 1, and then I could ask you, what is the velocity of the fluid at point 2? Well, all you have to do is measure the cross-sectional area of that pipe at point 2, and then with this equation, you can tell me the velocity of the fluid at point 2. Okay, so this is kind of the useful continuity equation that you use for a lot of problems. Okay, so that's just summarizing that problem, that equation, and so just make sure you know that. It's one of the equations on your equation sheets. Make sure you understand it conceptually. Okay, and so when you're solving problems in fluid flow, anytime you have a pipe which is changing in size, the first thing you should think is continuity equation, right? So a type of problem you could see is you have, the volume flow rate, the speed of the water at point 1, and I want to know how fast is the water flowing at point 2. Okay, so you have to bring in that conceptual understanding. The flow rate must be constant throughout the pipe, right? If 5 gallons of water is passing point 1 every second, 5 gallons of water must also be passing point 2 every second, right? The flow rate must be constant. And the second concept is, if the pipe is getting bigger, in order for the flow rate to stay constant, the fluid must actually slow down, right? In order to keep the flow rate constant. And so once you realize those two conceptual ideas, we can write down the continuity equation. We can recognize that we can rewrite the volume flow rate in terms of area times velocity. I can rewrite my area, if it's a circular pipe, as pi r squared. I can rewrite the area for point 2 as pi r squared. And now if I know the radius of the pipe at point 1, if I know the radius of the pipe at point 2, and I know the velocity of the pipe at point 1, I can figure out the velocity of the fluid at point 2. Okay, so that's how we solve that type of problem. And here's a quick simulation that will help you play with that. Let's see here, let me get it going. Oops, this one. So here we have a pipe. The volume flow rate is 5,000 liters per second. I can actually measure the flow rate everywhere on the pipe in this circle and see that it's 5,000 liters per second everywhere. And then let's see what happens when I make the pipe a little smaller. Okay, you can visibly see that the water is now flowing faster through that part of the pipe. And if I move this flow rate everywhere, I can see that the flow rate is not changing. It's 5,000 liters per second everywhere, even though the area of the pipe is changing. Okay, so in this region, the velocity of the fluid has to be faster in order to keep the volume flow rate constant. If I made the pipe bigger, the flow rate has to stay constant, but the velocity of the fluid then therefore has to slow down. Right? So again, the flow rate has to be 5,000 liters per second everywhere. The flow rate is still 5,000 liters per second here, but since the pipe got bigger, the fluid had to slow down. Okay. So here's one more clicker question for you, and again, this is just conceptual, so think about it on your own. And now we have a constant radius pipe that's flowing down a hill. So how does the velocity of the water at point A compare to at point B? Is the velocity of the fluid greater at point A than point B? Is it the velocity of the fluid greater at point B than point A? Or is it the same in both locations? Okay. And the answer here is C. Okay, so this may be a little bit surprising that the fluid flowing down the hill is not speeding up. The fluid is moving the same speed at point A and at point B. Right, it turns out the only thing that changes the fluid speed in a pipe is changing the area of the pipe. Okay, and let's think about this again from our continuity equation standpoint. Right, this pipe is completely filled with water. If I put 1 gallon of water in this side of the pipe, 1 gallon of water has to come out the other side of the pipe. Right? There's no room in this pipe to fit another gallon of water in it. If I put 1 gallon in one side, another gallon has to come out the other side. So that means that the water in all parts of this pipe has to have the same volume flow rate. It also means, since the area of the pipe is the same everywhere, that the velocity of the fluid has to be the same everywhere. Okay. A nice way to think about this is just as thinking of a pipe filled with a bunch of solid objects, like fill the pipe with golf balls. Right? If I put 1 golf ball on one side of this pipe, a golf ball has to pop out the other side of this pipe. And every single golf ball in this pipe has to move at the same speed. Right? The golf balls can't speed up going down the hill because there's all these golf balls in front of them. Right? It's the same thing with a fluid. Right? The water in this part of the pipe can't speed up down the pipe because there's all this fluid in front of it. It's incompressible fluid. Okay, so let's do one more clicker question. We have a pipe with radius 2r at point P, and then the pipe has a radius r at point Q. And so the question is, how does the fluid speed compare at point P and point Q? All right, so take a moment, pause the video, try to think about the answer here. Okay. And here's the answer. The answer is A. The fluid is moving 4 times faster at point Q. Okay. The pipe is getting, the area of the pipe is one thing, but the radius of the pipe is getting half as big, but the fluid speed is getting 4 times bigger. I think a lot of people commonly select B for this answer, right? Because you're thinking of the radius is getting half as big, that means the velocity has to get twice as big to keep the flow rate the same. But remember, this is area in this equation, not radius, and area depends on radius squared. Right? So if I'm making the radius half as big, I have to square that. Right? So this becomes 1/4 the area, so the velocity has to be 4 times larger. So that's it for this video.